Welcome back to my course Aspects of Biochemical Engineering. Now, in this lecture, we want to discuss the kinetics of the homogeneous chemical reaction, and as you know that I told you previously that chemical engineering is kind of basis of the biochemical engineering. So we try to understand the chemical reaction, how this chemical reaction we can express, mathematically express, how different kinetic constant can be estimated, and then initially we discussed the irreversible reactions, and then we will discuss the reversible reaction, and after that we will also discuss the chain reaction, because if you look at the biological process, we have seen that mostly the biological reaction, they are reversible in nature and they are chain reaction, because if you look at the metabolic pathway, several steps of reaction take place, A to B, B to C, C to D, like this. So those should be understood properly before we go to the biological process. Now, if you look at this overall the chemical process, how it looks. Now, chemical process, we have these raw materials. Initially we have raw materials, then these raw materials undergo some kind of physical treatment before it goes to the chemical process, and after chemical process we do some kind of purification, what we call physical treatment steps, then we get the product, and some of the things we sometimes we recycle back to the system. Now, the chemical reaction can be classified in two different ways. One is called homogeneous reaction, and another we call heterogeneous reaction. Homogeneous reaction means when the reaction takes place in one particular phases. So, we have three different phases. We have gaseous phase, liquid phase, and solid phase. If the reaction takes place in one particular phase, we call it homogeneous reaction. Now, mostly in case of homogeneous reaction takes place either gas and liquid phase. Now, in case of heterogeneous system, the reaction takes place more than one phase. That means either gas, liquid, liquid, solid, like this. At least more than one phase present in this reaction. Now, basic difference between the homogeneous and heterogeneous reaction is that in case of homogeneous reaction, the reactant, they are freely interacting with each other to give the product. Now, in case of heterogeneous system, one phase supposed to come in contact with the other phase, and then and only then reaction takes place, and after the reaction is over, the product has to diffuse from that phase to the other phase. So, that diffusion problem is a additional problem that we have in case of heterogeneous system. Now, so homogeneous reaction, we have the examples of this sulfur dioxide. When it in presence of oxygen, it produces sulfur trioxide. This is occurred particularly in the sulfuric acid production process. You might be knowing this sulfur trioxide in presence of water, it produces sulfuric acid. Now, when sulfur dioxide is oxidized further to sulfur trioxide, this all are gaseous phase. This is gas, this is gas. So, reaction occurred in the one particular phase. Since the reaction occurs in one particular phase, we call it homogeneous reaction. We have another example is LPG. LPG is the liquefied petroleum gas, and when we part and it mostly contains the butane, and when butane we burn it, then it produces again carbon dioxide and water, and carbon dioxide water also gas. Now, heterogeneous reaction, we have the examples of burning of coal, and the coal is the solid material. In presence of oxygen, oxygen is a gaseous material, the ultimate product is carbon dioxide. So, here simultaneously mass transfer and the reaction occurred. As I pointed out before, one phase has to come in contact with the other phase, and then the reaction take place. So, two things simultaneously take place here, and if the rate of diffusion is more than rate of reaction, then we call it reaction controlling. So, if we want to improve upon the process, then we shall have to improve this rate of reaction. Now, if the rate of diffusion is less as compared to rate of reaction, then diffusion is the controlling. So, we shall have to improve the diffusion rate. Now, if you look at the rate equations, it's like this: the AA plus BB equal to RR into SS. Let us, this is product and this is your reactant. Now, rate of disappearance of A minus RA, it is usually expressed as minus. The reason is that it is disappearing. Now, if you plot the concentration of product, concentration of raw material, the substrate with respect to time, always it will like this. And why it is decreasing with respect to time? That means rate of degradation of Ca, that always should be negative, because it is the negative profile that we have. So, this is why, that is why we have written minus R A. This minus R A equal to dN by V. N is the what moles of A. So, concentration, what is concentration? Concentration is nothing but mass per unit volume or moles per unit volume, moles per unit volume. So, this is here Na is the moles of A and V is the volume. So, V is the constant. So, it is comes out, and this is this is expressed as dNA by dt into V. So, again, when you do put it like this, then we can express in terms of concentration, we can express minus dCA by dt. This is moles per liter per second. Now, in the previous reaction that we have seen, that is A plus BB equal to RR plus SS. Now, here how you express the rate of the reactions, that that minus RA into A divided by A minus R equal to minus RB by B, and the minus R by small r minus S RS by S. The rate of reaction is influenced by the composition and the energy composition and the energy of the material. Energy means temperature, light intensity, and the magnetic field intensity. This is so rate even in this any kind of reaction we can express like this. Now, here that suppose that we have taken a very simple reaction A to product, A is the reactant, and give the what is the how we can express the rate equation minus R equal to K. K is called the rate constant. This is called rate constant, and this is called order of reaction. Order of reaction. So, these are the two constants that we have. So, K into now K again K depends on temperature, and K depends on temperature, that can be expressed by the Arrhenius equation. This is minus EA by RT. So, if we put it here, so the whole equation looks like this. So, this is the Arrhenius equation, we put it here, this equation looks like this. Now, this is the Arrhenius equation I told you, this is Arrhenius equation. Now, the rate of reaction again directly proportional with K. So, since the rate of reaction is proportional to this is inversely proportional with T 1 by T, the same constant time, that is inversely proportional with this. So, Now, if you take this Arrhenius equation into consideration, then we will find at two rates this ln minus, because since it is proportional to k, because as I told you, this minus R A equal to k into C A to the power n. Am I right? So, so it is proportional to this. So, in the Arrhenius equation, we have also written this equation k equal to a to the power e to the power E A by R T. So, so I can write that RA2 by RA1 equal to ln K2 by K1, because this is at the particular different temperature, it will differ, and this is equal to T1 by T2, this, since it is inversely proportional with time, and this is, if you take this into account, then we will get this particular relation E A by R equal to 1 by T A minus 1 by T2. Now, temperature dependence on the reaction is determined by the activation energy and temperature level of the reaction. So, this is very much clear from this from the next slide, that I can show you here. We have plot, this is the log plot. You can see that this is 10, then this is 100, like this, and a double we can do that. This is not normal plot. So, and this is the normal centimeter plot that we can have. So, this is the equation that we have, that ln K2 by K1 equal to E A by R 1 by T1 minus T2. That we can do it very easily, because if you know K equal to A e to the power minus, I can show you in other way. That if you consider the K1 equal to A e to the power minus E A by R T1. Let us assume this is the T1 temperature, and K2 equal to A e to the power minus E A by R T, this is T2. Am I right? Now, if you divide, if the K1 by K2 by K1, then what I can write, e to the power minus E A by R T2, this is the E A, sorry, this is the E A, R T2 by e to the power minus E A by R T1. So, we can now this is equal to what we can write, this is equal to e to the power minus E A by R T2 plus E A R T1. Am I right? Then you can take it upward. Then ln, if you take ln K2 by K1 equal to, then I can write this is equal to, you can E A by R, you can take common, though this will be 1 by T1 minus 1 by T2, like this. We can easily write this equation, is not very difficult. This is how this equation has come. Now, here we want to focus one particular point, that we are interested to show you this portion. Now, if you look at this lower tape, this is 1 by T. Am I right? If I 1 by T, this is 1 by T is higher. That means it's the lower temperature. At lower temperature, that if you look at here, that is the del T is 87 degrees centigrade. For doubling the rate of reaction is this. Now, here if we in the higher temperature, the K value changes more as compared to this value. Here at low temperature, your rate of the K value doesn't change much. You know that if you see that for 87 degrees centigrade, you have this much of change, but in higher temperature, this you require more temperature to change the K value as compared to this. This has been found that this from this particular Arrhenius plot, that we can easily find out this. Now, temperature sensitivity of reaction, that is determined with the help of Arrhenius law by semi-log plot. I have already shown you. This is if you plot ln k versus 1 by t, that gives you the simple type of this slope will give you the value of A by R, and here R is the gas constant. So, if you put this value, you can easily find out the value of A. The reaction with the high activation energy are very heat temperature sensitive, and reaction with low activation energy relatively temperature insensitive. So, if the activation energy plays very important role as per chemical reactions is concerned. Any given reaction is much more temperature sensitive at low temperature than the high temperature, that we have seen previously, that at low temperature their change of K value is more as compared to high temperature. And from Arrhenius law, the value of frequency factor does not affect with the temperature, because that remain constant with respect to temperature. Now, question comes, how we can determine the value of rate constant and the order of reaction. So, this is the equation that we have. The rate of reaction can be just A to B, if there is a rate of reaction and K is the rate constant, it can be expressed like this. Am I right? Now, if you take a log, natural log ln minus dCA by dt, this comes at the ln k by this. Now, in case if you plot, this is log graph paper, this is ln minus dCA by dt, and this is ln CA if you plot, then you will get a slope, and this slope will give you the value of n. Am I right? And this intercept will give you the value of ln k. So, you can find out your k value as well as your n value, both k value and n value, you can find out any kind of chemical reaction. This is what we explained in this. So, here also you see that similarly we can find it out from the slope, we can find out the n order of reaction, and intercept we can find out the value of k. And so, central differential method, that this is another very interesting, the differential technique. Suppose we want to find out the substrate concentration rate of substrate degradation. I can give the example. I can give the example. Suppose in a reaction, suppose Ca is decreases with respect to time, you have profile like this. Now, if you want to find out minus dCA by dt, how you can calculate? You can calculate the Ca n plus 1 minus Ca n minus 1 divided by 2 del t. So, you suppose you have T1, the T value and Ca value. So, you have different value here. So, you can find out this is the number of sampling point n, this is 1, 2, 3, 4 like this. So, you can Ca n plus 1, suppose you want to find out this, that means you have to take the value here, and minus 1 means 0 hour you have some value, you have to take the value of 0 hour, and del t is the time difference. This is the 1, 2, that may be in hour, maybe in minutes, the difference you have to give. You can easily find out the rate of change of substrate concentration, rate of change of product formation, all you can estimate with the help of differential technique. This is called the differential technique. Now, simplest reaction is the first order reaction when n value is 1. First order reaction means n value is 1. Then we can write this equation like this. Now, this equation I can write line minus dCA by Ca equal to k into T. Am I right? So, this is what this is equal to ln d ln Ca this is equal to K into T. So this is minus, so we can do the integration Ca to 0 to Ca. So we can write this is ln Ca by Ca0 minus equal to K into T. So I can write T equal to what I can write the T equal to will be what? Now I can write Ca equal to this is e to the power minus k1 t. So I can write Ca0 e to the power minus k1 t. So we can easily at any time, any point of time, if you want to find out the concentration of A, that you can find out this correlation. So this is like this. So, so this correlation we have what I have shown you. This you can solve it very easily. Again this conversion I can express in other term also. With respect to Xa is the fraction of A that is converted. This is Xa. Xa is expressed as 1 minus Ca by Ca0. That means Ca by C0 is the fraction that remains after time t. The 1 minus means fraction that is converted. So with that respect, if we convert the same equation, we can convert it like this. How we can convert? Suppose dCa by dt, I have written what K into Ca. Am I right? So what is the Ca? Here we have seen that K equal to Ca0, initial concentration of substrate 1 minus Xa. And what is that? Now if you do that dCa, then what will be? This is 0. So I can write Ca0 is constant. So this is equal to dXa. Now here if you put this value here, dXa, the Ca0 will cancel, we will get this equation. So this is the final equation we will get in this form. Now if you plot the ln this 1 minus Xa of versus t, we will get straight line plot, and slope will give you the value of K. Slope will give you the value of K. So we can easily, in case of first order reaction, we can find out that K value of the chemical reactions. Now question comes, what will happen when we have the fractional when we have the nth order reaction. We talk about the first order reaction. Now nth order reaction, we have the expression like this, and this we can write in this form. This is where n is not equal to 1. This we can have this expression, we can differentiate, we can write this expression like this. Now this equation may be simplified in this form, and finally we can write this equation in this form. This is the F is the fraction, that is the F is defined as the Ca by Ca0 fraction of reactant converted at time Tf. Now in case of F, if we substitute F by T half, what is T half? Is the half life of a chemical reaction. Half life of a chemical reaction, how we define? That where the half of the substrate that is converted into product, and that time if you put in this equation, we will get this particular equation. Now this is very interesting, because if you look at this, that when order of reaction n equal to 1, now if you come back here, if your n equal to 1, this will be 0. Am I right? This will be 0. N equal to 1. This Ca will be 0, and if Ca to the power 0 is there, then T half is independent of Ca. Am I right? So here ln Ca0, it will be constant like this. Now in case this is more than 1, then it will be negative. More than 1 negative, then it will be inversely proportional with this T half. And in case of positive, it will be I told you, if n is positive, then now here if n is less than 1, in case of n is less than 1, then what will happen? This will be positive. Then T half is directly proportional to the T half. What I can write that here T half will be directly proportional to C A. So as the T half changes, then with C A value, then this also will changes like this. So this is what I want to point out. This is a very good relationship that we have. Then we have other type of reaction. We have the parallel reaction that can be expressed like this. This is key bond minus dCA by dt equal to rate of this conversion of R and rate of conversion of S. That can be expressed like this. We can take common Ca. We can write this. Now, in case of autocatalytic reaction, you see that what is autocatalytic reaction? Where the product acts as a catalyst, and it is an example of our microbial system. In the microbial system, when we get the product, the microorganism itself again it produces more products. So it is kind of autocatalytic reaction. Now here how we express that? This can be expressed like this. You see that RA equal to K into Ca plus Cr, because it is proportional to like this. What is C0? C0, if we assume the concentration of A plus concentration of R, so we can write this is Ca0 plus Ca0 and Cr0, that should be equal to constant. So this expression we can write in this form, final expression. This is equal to Cr equal to C0 minus Ca. So by rate of substrate conversion we can express like this. So in conclusion of what I want to tell, that in the reaction kinetics, what we basically deal with, that I told you that whatever reactions we have, broadly it can be classified into two ways. One is called that homogeneous reaction, another we call heterogeneous reaction. Now homogeneous reaction, where the reaction takes place in one particular phase. We have three phases. We have gas phase, we have liquid phase, we have solid phase. Now mostly the reaction takes place either gas phase or the liquid phase in a homogeneous reaction. But heterogeneous reaction, where the reaction takes place more than one phases. The major limitation of this process is that one phase should come in contact with the other phase, then and only then reaction takes place. So this is the limitation of the so diffusion is a very important aspects of this heterogeneous. So diffusion reaction both simultaneously. When the rate of diffusion is less, then as compared to reaction, then diffusion is a controlling factor. When rate of diffusion is more as compared to rate of reaction, then rate of reaction is the controlling factor. Then question comes that how we can write the expression of the chemical reaction, that we come across two different constant, rate constant K and order of reaction. We discuss how it can be determined. Then different types of this irreversible reactions we have side reaction, we have autocatalytic reaction, how mathematical expression can be done, how we can determine different rate constant, K value, both in case of first order reaction and nth order reaction. I try to explain. Thank you very much.